Hello, physicists. My name is Gavin Baker. I'll be analyzing the energy of a weight on a spring using the energy principles and Newton's laws. So, I use Tracker to track the motion and GlowScript to create a computational model to predict motion. First, I'll go over the results and explain what concepts support the observation. Later, I'll be comparing data and explaining any discrepancies. This experiment is relevant because creating a computational graph that simulates motion can predict the future, which is very important in various applications. Here is the software I use to determine the observed data. I track the position of the origin of each frame to obtain this data. As you see, the weight on the spring oscillates in a figure 8 motion. Both of the graphs show waves in X and Y direction. I tracked frames after the weight was released, since it accelerates in the very beginning. For tracking, I set the origin on the fixed point and the axis perpendicular to the ground, since that is where it is suspended. Here is the code I use to produce the predicted data. The time step is 1/200th of a second to match the observed time step. And using the observed data, I calculated the spring constant and the relaxed length of the spring using the formula T equals 2 pi times the square root of m divided by k. And these energy equations down here is how I calculated delta E and the rest of the data. And as you can see, the spring oscillates in a figure 8 as time goes on, with delta K being very small, and delta U gravity and delta U spring going up and down, canceling each other out on the maximums and the minimums. Both the tracker data and the computational model display a wave as time passes by. This shows that the velocity and momentum of the spring is non-constant and always changing. This makes sense because as the spring stretches, it slows down and compresses back. Everything is included in the system since delta E is equal to 0. Newton's second law is force is equal to mass times acceleration, which of course applies to this. The energy principle is crucial to making the code. The change in energy is equal to all the other energies in the system. For my computational model, I determined the motion of an oscillation with changing momentum and energies. The observed motion and predicted motion from the computational model are very similar. The x-graph matches almost perfectly. The y-graph is very similar in shape, but slightly smaller in magnitude. Perhaps the tracker data is slightly off because it is more difficult to track a smaller object with greater precision. Multiple tests and more accurate data collection would help future experiments. There are 3 energies that are added together to equal the change in energy, which are the gravitational energy, spring energy, and kinetic energy. All 3 are constantly changing, with kinetic energy changing the least. And down here are the different equations I use to calculate the change in energy. I use the momentum and energy principle to calculate the change of energies of the spring, and I use this for the code. The momentum principle equations to the right determine velocity and position, and the energy principles on the left are used to find the change in the different types of energy. So what? The energy principle is satisfied since delta E is equal to 0. This means all the energies contained within the system, and you can see that the energies balance each other out. For example, when the gravitational energy is at its maximum here, the spring energy is at its minimum. Taking 2 points at the top of the waves of the x-graph results in a period of 1.6 seconds. Doing the same for the y-graph results in 1.5 seconds. The period is slightly smaller for the y graph. This is because the energy changes slower in the x direction because the path is much wider. Thanks for watching.